Okay, thank you for introducing me. My name is Yeong-Dae Kwon, and I'm from Samsung SDS in Korea. And I thank the organizers for inviting me to this talk. Very honored. So, who are we? So Samsung SDS is actually made up of two large divisions. One of them is the logistics. So, you want to ship all the Samsung-made like cell phones, TVs, whatever, from the factory to all over the world. So that's one part. But actually, I belong to the other group, IT division, where we set up servers, run cloud services. So in a sense, it was unnecessary to put this figure here, but I just wanted to brag about it. We don't have that much connection yet. So my team's work, we work on the machine learning on, let's see, I can't really, sorry, let me just bring this up here. Okay. So we work on the machine learning on combinatorial optimization. Like we have a big team who does the AI research, and my small team belongs to this group, and we work on the combinatorial optimization. And possibly in the future, we can make some applications to logistics or, more practically, the cloud server optimization. So for the past 3 years, we've been quite lucky and productive. For some of you who are not really familiar with the machine learning community, the NeurIPS, iClear, those are like top tier ML conferences. It's a big honor to be able to present there. So that's just like publishing in machine learning community. So we have been publishing every year, and in 2020 we published POMO that Kevin was keep referring to. So that was based on Walter's paper, and we really thank. Where is he? We really thank him for the nice base work. So, and then the next year we published a metrics encoding network, which we call MATLAB, which I have a slide in the next slide. And then the next year we did the inference technique or the search technique that Kevin was talking about in the last talk. So just to tell you a little bit about the MATLAB, we wanted to be able to use the distance metrics that's usually given for routing problems sometimes, because you can't always just use the coordinates. Sometimes you have to rely on the distance matrices. So what we did was we designed a neural network in a sort of a new design where we can input the whole metrics and then get the encodings of the from cities and to cities. So, and after that, you just follow what Kevin was describing. You generate route one by one and create a solution. So this is a nice little demonstration with TSP, but you can always use the same technique on CVRP or even VRP-TW. So that was that we knew, and when the vehicle routing competition came up, like we said, okay, let's go there and do some work. And it turned out that this was a very valuable experience for me. It was sort of like a wake-up call. Like, at the end, we did very great. Like we were very satisfied with our third place, and then we got the jury prize for we used reinforcement learning, and maybe we were the only one. I don't know. But during the process, we realized that, using our techniques to real world problems, there are lots of complications, and we better find some better way to accommodate all these problems. So let me share some of our experience, the problems that we experienced during the competition. So as I was saying, we could just use the old algorithm to generate solutions to the time window vehicle routing problem. But the very first problem we had to tackle was that we were given only 250 sample problems. And there was a discussion about having to have a generator to be able to train your neural net. So we could not really train our neural net based on just 250 problems that were given. So the optimal way would be making a generator, problem generator, that has some kind of hidden distribution that fits the sample problems. But that's always tricky. So what you see here, I guess I didn't really explain this, this is the training curve. So using the 250 problems, you train your neural net and see how it does. Well, we actually use only 200 of them to train and see how it performs on the other 50 problems. And then you see that the training curve goes down, but on testing, you don't get any improvements. That's the overfitting. So that was one problem. And then there was the problem with solution quality. We knew from the beginning that we would not be able to beat the baseline HGS with our generic algorithm, because we never got to HGS level anyways. With TSP, we had a 0.1% gap. With CVRP, we had 1% gap. And we did some experiments with 250 samples, and with VRP-TW, we had about 5% gap. So, but why did we even bother? Because we knew that we can have an advantage in a sense that we create these solutions in one shot. There's no searching. We just let the neural net create a solution, and we have, quite a good solution, not ideal. And then, we can start from there, because HGS, they use random solutions to start from. So we have a, head start if we use these solutions, right? So that's what I was thinking. And it turns out it's not really true. So that's what we get when we run HGS, starting from the solutions that our neural net made. And this is the random solution started HGS. So yeah, we're doing fine up until 1 or 2 seconds, but then there's no benefit whatsoever. So doomed. Yeah, that was a sad day. Yeah. So that all this kind of experience got me thinking we really need to shift our framework. If we want to use machine learning to gain some real gain on real problems. So this is the approach we've been taking to, and it was introduced before, end-to-end sort of construction approach. We were going to replace the whole heuristic algorithm, or MIPs, with the neural net that creates a solution. So, this works, but what if we can do this, right? Let's not just dump the heuristic algorithm, which we know works great. Let's just use our neural net to help the heuristic algorithm so that it can get better solution. So this diagram has been introduced yesterday. So this is the same, same picture in a different configuration. So I thought okay, this is going to help a lot if it works. because there's so much possibility on what you can do on this select part. The very first thing you can think of is the hyperparameters. Like, why don't we have a hyperparameters that adjusts itself as you solve your problem? And then, there are lots of other heuristics that you can play with. So that's the way to go. That's what we thought. And as a machine learning engineer, like if you see something like this, you immediately come up, like this image comes up in your mind. Like, this is the Atari game. Some of you may be familiar with it. Some of you may not. Like, there's a nice demonstration of YouTube video. Like, this is like standard reinforcement learning sort of demonstration. So like, if you train long enough, the AI learns the trick where it breaks the side part and then let the ball go and like get great score. So anyway, so this and this, they're basically the same thing. Like, you have a screen, and then you let your neural net make a choice, and then it acts on it, and then it goes on, and then you let the neural net make another choice, and then you continue, and at the end you get the score. And then the reinforcement learning, you try to get better score by training this neural net. And there's like millions of researchers, not millions, but they're working on this nice RL techniques that makes this work. So why don't we just go there, find algorithms that people have been developing, and then just use it on the heuristics. So that was a very naive idea that we had. So I'm going to present two big problems with that kind of approach. So first problem is with the states. So I'm going to explain what that means. So this is the basic RL framework that many of you are familiar with. You have an environment, state goes into the agent. Agent is made of neural net. It gives you action. So because it's a neural net, it has a fixed structure, and its input needs to be vectors. So that's no problem for these kind of standard benchmark RL problems, because for these kind of these are Atari games. Like you have a screenshot image, n by m pixels. That doesn't change as you go along. And then these are another benchmarks that people use for RL. These are like they're called Mujoko. It's like robots in 3D world where you try to make them move fast or whatever, jump. And that's also, they have no problem with the states, because your state is given by the position and velocity of all your joints. So it's fine for these problems. For the heuristic algorithm, like what would be the state? Like it has the complete set is all the values of the variables that you use in your algorithm at one point in your time. So I mean, and then sometimes variables disappears, like the new variable you create, like you can't really use that as a state. Like you have to engineer your state, and then it needs to be good so that it sort of represents what your state is. But then even if you make a very good engineering, some information will be lost. And then now it becomes a partially observable problem. So like and that makes it very hard. So I told you about the first problem. The second problem of applying RL on heuristics is this critic network. They're also called value networks. So I've been only showing the RL agents like this, but usually the mainstream RL researchers use this actor-critic type sort of agent. So what these does is that the actor tells you what actions to make, and the critic tells you how good that action was. And the output of the critic is used to create a loss. Yeah. And that's been very successful in the RL community, and that's like the standard thing that you do. Like everything you probably see are sort of like, variations of this actor-critic the structure. So what would be the critic if we are going to use this kind of framework? Like what critic does, it predicts the final score. Like given a state, tell me how good you will be at the end of this algorithm. That's what critics should do. And I mean, is that even possible? So why is it hard? Why is it hard? Well, the first, problem solving wise, like at the beginning, it's hard to predict what the final score will be, like because it's NP hard. It's a hard problem. Like you don't know what your sort of optimal solution is until you solve it. I mean, and you can't really sometimes solve it. But so problems are hard, and even during the solving process, the heuristics you use a lot of randomness. So given a state, it's hard to tell like how you will perform as you go along, unless you're really at the end of the process where you're sort of like you're there. And application-wise, critics work for those Atari games because they are usually, they're always trained on one particular game. So like, they're just solving one thing. And if you see the score, like you did well or you did not well. But what we want to build is not an agent that solves one problem. We want to build the agent that solves many different problems with many different optimal solutions. So then, if you want to do that, it's hard because like you can't really tell if your agent did a good job or bad job, because you don't know the optimal solution. So critic network is pretty hard to build. So here's sort of like a little demonstration of how difficult it would be to create a critic. So as I was saying, if you have a critic, it needs to tell you how far you are from the optimal. And these are the graphs, the performance of the HGS on CVRP 200. So sometimes, depending on whatever seed that you studied with, it converges sort of the optimal sense. But then, you get these cases where depending on what seed you study with, like, you're all over the place. Like you might end up, never getting to near the optimal. So, and if there is a good critic, what it should do is, like, let's say you're here and like the critic should say, you're not really doing very well. Like you're going to drop down a lot. Or sometimes, like if you're here, like the critic should say, like, there's not going to be improvement. You're almost at the optimality. Like, can a critic do that? Like, I find it very difficult to believe that that's possible. So here's a little thing that I also did. So let's take a step back and let's do something easier. Like instead of predicting what how far you are from the optimal you are, like let's try to predict the variance of the final scores from different seeds. What I mean is, like, having generated all this, like now you can see like what the variance are for different seeds, and that is made into one graph here. So like as you run your algorithm, differences will make different solutions, and these are the variants. So these ones are the hard problems where you need to be lucky to get a good solution, and these are the ones, the easy ones, like no matter what, you're going to get like a very good solution. So can you create a neural net that predicts like how hard your problem is? Like it feels like much easier problem than having a real critic. So if we do that, then it's probably going to help me, because if I know that I'm solving a problem that's very difficult and it's very like seed dependent, like I could try to do more exploration to get to the bottom of the graph. Like this information will help me. So can I build a network that does it? And it turns out no. So it's like obvious no. So this is the training and that's the test. I say 10,000, but it may have been 100,000 or more, I don't remember. Like you spent really long time collecting all the data. But then using all those training data, we try to train our thing, and I mean, it's not even overfitting, right? Like it's just not learning anything. So it seems like there's no pattern to learn. So, and it's not the fault of our deep neural net, because I'm using the structure that produces very good action sequences. So it's not really the capacity of the neural net. It's just there's fundamental difficulty of predicting the behavior of the HGS algorithm or other heuristics. And just a little extra proof that that result that I had was because I did something wrong. I want to mention AlphaGo. And as some of you might know, AlphaGo also uses actor and critic. And the critic for AlphaGo, what it does is, I mean, it's the same. It looks at the board, empty spaces, and it tells you what the score is for each position of your move. So if the critic was good, then you can just tell what your critic tells you, just find the best position and just do it. But that's not how AlphaGo works. Like you have to do extra search using the information that you got from the actor and critic. So basically what I'm trying to say is, building a critic that's reliable, that's really hard. So I think I have 2 more slides left. So can you do anything without using critic? The answer is yes. And you can just use the actor, or in this case, it'll be called policy network. So you just use policy network and try to do the thing that I just have described. It's possible. You make a state out of your algorithm, and then let the policy network tells you what selection to make without the help of the critic, and that's possible. The only problem is if you do this without critic, then you have very bad sample efficiency, and they are prone to fall into local optima. So this is not very popular sort of a solution in the RL community, but it seems like if you can't really use critic, this is the way to go if you want to use reinforcement learning. And one little tip, just for those who are familiar with the PPO algorithm, PPO is used for actor critic, but it can also be used for just the policy-based RLs as well. So you should consider using PPO, which will help you a little bit with the sample efficiency. But so yeah, that's possible. It's in theory, but in reality, I don't know. So let's let's go back to what I was trying to do. So let's take the GA or HGS for example. Like, there's going to be a pool of solutions, and you do a step. You do crossover, mutate, you select, and then you do it repeatedly, and then you get solution. And we want the neural net to sort of like help you with the decisions you make in this kind of steps. Like one example I was thinking of was this binary tournament thing for HGS, because in the competition, what we did was we replaced binary tournament with the K-way tournament, but that was with the handcraft scheme. Like we sort of like, okay, let's use something, and then after a while, let's use something like by hand, and we just try to tune it by hand. But if the RL works, like the neural net might be able to tell you what the optimal K value is for the tournament, right? So that would be great, and I'm sure like all of you can come up with like something that you can just plug in, like it's nice to have something that automatically finds like optimal values for you. But this is a work in progress, and I was saying like this is very hard. One reason is because the actions you're making are too many. Like usually, I don't know, depending on the algorithm, like it can go like 10,000, 100,000 steps. So like you do it like 100,000 steps, and then you get one reward. Like it's hard to know which one really counted. So I mean, yeah, it's hard. I mean, so you have to sort of like find a way to go around it. And then I was saying the designing of the states, that's also hard. You have to think really carefully to what to put into your network and then get good results. So I'm not saying this is going to work. I'm just saying like, this could work, but this is hard, and this may be a very bad approach as well. So sorry, I'm not giving you any like good information whatsoever, but so that's all I prepared today. Thank you.
Any questions for Yeong-Dae?
Yep.
Is it possible to use a critic or just a loss function in general, where you just assume the best score is 10% lower than your current known best score?
I don't think it's going to help you with the training if you just do that. Like the critic really needs to be intelligent. Like that's why you use critic to help you with the training. Like if you just say like you're going to get 10% better, like it doesn't really contain any information. Because like you need to know which action. Yeah. So it's not the ML. It's not the reinforcement learning way. Yeah.
It's not a question. I was just going to say the negative results are the best results. I learned a lot more from them, and they're so rare. So it was great.
Thank you.
There's a journal that publishes only negative results. Forget the name of that journal. Only negative, which is useful to know, because people only publish what we know, what is nice, and not all this effort that is put.
Yeah, I was really hoping that this can help other people not to just follow the wrong steps again. Yeah.
Yeah, we had a similar trajectory as you. During a couple of years, we tried with the student to integrate neural networks, so the heat maps that Water developed and also that you use, to try to direct local search on define what is the granular neighborhoods that we use, that's what move you should try.
Yeah.
And it was quite unsuccessful, which led us to publish a paper where we are writing that it was an overkill. Because distance was doing exactly the same job. One thing I remarked is when you presented the negative results about the ability to predict the variance, you use a certain data set. Was it the X set that has like 10,000 instances with the same distribution, like I think water generated at some point, the most used one? Or is it the one, for example, that Quiroga and Potters generated? Because those instances are quite diverse. They have roots of different size, capacity, settings that are different. And I think there is more chances then that you have features and characteristics that permit you to better explain the difference of variance in a richer data set such as the one that Quiroga.
Yeah, I think that's good. Yeah, that's a good point. Like for this, we just generated the random position in a unit square.
Yeah, that is really, like, there's not much structure.
Yeah.
And what kind of model did you use for that? Because sometimes I have a feeling that specific structures, like a few customers, can be difficult for the method to discern what's the right thing to do in a certain region. So it could indicate that, for example, something like attention-based mechanism could be nice at finding these structures.
Possibly.
Is it something you explored?
Not really. As soon as I got this, I moved on.
Okay.
Yeah. Yeah.
Yeah, if you go back one, I noticed too that down at the bottom, there's a blue line that's moving upward rather than,
Oh.
you know, they're all kind of jiggling a little bit, but, you know, that's gotta be concerning,
No, that's the part.
you know, in terms of trying to find a predictor.
I'm not an expert on the topic, but have you ever considered the possibility of that not having too much diversity in the training set, as you mentioned, can be actually bad? I'll give an extreme example, this ChatGPT. So ChatGPT is good because it's trained. So it seems that the ability of ChatGPT to do poetry helps on math, and then this helps on so in the very big, broad analogy. So suppose you are training with a very diversified data set, like this Quiroga set, then perhaps the neural network can become smarter than if it's only trained with random data.
You have a point there. That's possible, but I want to point out that the ChatGPT model is so large, unbelievably large, larger than the models that we use in routing problems. So, and then the training data they use, it's remarkable. So it's possible. I mean, ChatGPT can do everything. Like they will just conquer the world anyway. But so, yeah. But right now we're stuck with some limited size neural net model, and it does only what it does.
Any other questions? All right, let's thank Yeong-Dae.